we want to talk about the temperature modulated DSC. So not the conventional DSC measurement at all. And I just want to give you some information about the how we do the temperature modulated DSC measurements with our device, the Chip-DSC, and also what's the advantage, what are the possibilities, and how to practice these measurements. I'm Michael from Linsize. I'm here since 2017. And if you want to contact me, if you have special questions, feel free to contact me. You can find also the contact information at the end of this webinar. Okay, at first something about Linsize thermal analysis or Linsize Messgeräte. We manufacture many instruments for thermal analysis and determination of thermophysical properties. And Linsize, as a family-owned company, was founded in 1957. And our headquarters is based in Germany, but we are acting all over the world. And yeah, I think we're a pretty innovative I think we're pretty innovative. And so if you have some requests about special devices, and I'm sure we can adapt them to the customer requirements. So here you can see our complete product range. But of course, today we want to talk about the differential scanning calorimetry. And of course, it's also possible to couple all of them with some gas analyzers or other measurement systems like Raman spectrometers, cooling options, or sample robots, whatever. As I said, today we want to talk about the differential scanning calorimetry. Invented 70 years ago. It's still a powerful tool to give some or to perform some investigations in thermal analysis and on your materials. So I already mentioned we are talking about the Chip-DSC, and at first I want to give a short look out what's the special thing about the Chip-DSC. So all in all, it's a common heat flux DSC, and you can see the conventional DSC measuring cell here at the left. Just let me show you with the laser pointer. So what you can see here is the surrounding oven, and inside this oven you can find here at the left side the sample inside the crucible, and on the right side the reference on the crucible with the temperature sensors at the bottom. And yeah, this is how almost every heat flux DSC works. What we do with Chip-DSC is we converted this measurement cell or this measurement system. So now the reference is at the bottom of your sensor, and now it's fixed. So you don't need to use any reference crucible anymore. And also the heater is now inside. And yeah, not the complete measurement measuring cell is inside the oven. And the complete sensor, as you can see here at the bottom left, is pretty small. And due to this, we don't have so much thermal mass. And this is why we can heat up and cool down pretty fast. And this is pretty interesting also for temperature modulation. But I will show you the advantage later in the how-to or in the hands-on. As you can see, the Chip-DSC device itself has a really small footprint. So it's 20 centimeters in height and width, or length and width, sorry. And also it's possible to adapt many options like a Raman spectrometer, a camera, curing UV light, different cooling options. and also the sample robot, of course. As you can see here on the right side, it's also possible to give it in a big housing. So this is the Chip-DSC 100. You can see here on the right. And yeah, here you can find the sample robot and many options you can you can adapt to the Chip-DSC measurement cell. Another good thing regarding this Chip-DSC is, of course, it's possible, so it's pretty affordable. But I think enough marketing. Let's go to the measurements itself. So what you can see here now is a conventional DSC measurement of any polymer. So you can use the DSC at all in industry, teaching, research, whatever you want. So for quality management and so on. And there are many transitions you can detect with the Chip-DSC. What we can see here at the beginning of the heating run, for example, is the glass transition. And this glass transition is overlaid by a relaxation peak, here called the hysteresis peak. And at next, you can find here the cold crystallization, an exothermic peak. And after this, of course, the melting, and also you can find oxidation and the decomposition here in this curve. And also it's possible to detect something in the cooling run, of course, here in this case, the crystallization and the glass transition. What you can see here is some effects are overlaying. So it's not so easy to detect the glass transition without the relaxation peak. And also, of course, it's not so easy to detect the relaxation peak without the glass transition. So they will affect each other. And the same you can find for some materials for the melting and oxidation. So now we need a solution how to split these signals. And this is why we want to use the temperature modulated DSC measurement. So all in all, what do we do? The conventional DSC measurement is, for example, just a straight heating profile going upwards from room temperature to 300 degrees, for example, for PET, what you can see here at the right. And this is the black curve at all. And below you can find also the DSC signal, the black curve here in the lower part of this diagram. And now what we do is we modulate the rising temperature here with a pretty small modulation, but this is important, I will explain later. And this way we receive the red curve here at the bottom of this diagram. And due to this, we can receive much more information than in the conventional DSC heating run. So one information we could receive here is the specific heat capacity. So the specific heat capacity you can receive. So this is the heat that goes into the sample to heat it up for 1 Kelvin. I will explain later again. And so you can obtain much more information, as I already said. And here you can see, the CP, for example, of a polymer with a step here in the CP signal for a polymer at around about 70 or 80 degrees. And what you can also see here is the melting. Another information you can receive from the DSC measurement is the reversing and non-reversing part of the DSC measurement. So you can see it here at the right. At the top, you have the non-reversing curve, with two exothermic peaks. The total curve, of course, it's also possible. And with the Crelast transition, recrystallization and melting, and the reversing part with the glass transition and just the melting. So what you can see here at the reversing part, the recrystallization doesn't come up. Also, you can't find the melting itself and the glass transition in the non-reversing part. We will see this in our own, in our PET measurement later on. So now let's talk about some basics. Our normal or our conventional DC measurement often is performed with a straight heating rate. You can see here at the right, the black curve. And this temperature profile itself is defined. So the temperature is the start temperature, mostly room temperature, unless you have any cooling option, of course, then it's below. Plus the average heating rate multiplied by time. So this is basically what we do here. And now we added the modulation, what you can see here below. So basically it's the same for the rise of the temperature, for the average temperature. You have the starting temperature, room temperature or below for cooling options, plus the average heating rate multiplied by time. But what we add now is we have an amplitude here. So this is the amplitude of the temperature modulation you can see here, multiplied with the sign of omega and time. So this is how we receive the result here. This is basically just what we do for the temperature. Now let's talk about the results. As I already mentioned, the total heat flow could split it to reversing and non-reversing parts. So our complete DSC signal, what you can receive with conventional DSC measurement, for example, is basically the heat divided by time, as you can see here, the DSC signal. Now, the non-reversing part is this signal minus the CP multiplied by the average heating rate. And the reversing part is a calibration factor multiplied with the amplitude, omega cosine, and also here comes up the CP. So what you can see here now is there's no CP in the non-reversing part, but the CP is here in the reversing part. And this matched to our results. What you can see here, the CP is basically the same like the reversing part, just upside down. And here again, you can see the DSC signal you can receive and also the raw signal with the modulation. The CP itself is the amplitude of the DSC signal with a calibration factor omega and the amplitude of our modulation, what you can see here at the bottom of this slide. So let's talk about the specific heat capacity again. So the specific heat of a substance is the amount of energy that must be added to heat 1 unit of mass, whatever this is, of a substance for 1 unit in temperature. So just to give you an example, for at 25 degrees room temperature so far, the required heat to raise temperature of 1 liter of water by 1 Kelvin is 4,180 joule. So the heat capacity of water at 25 degrees is so far 4,180 joule per gram Kelvin. So this is basically what CP is, and what we can see here is the war signal again at the bottom of this diagram, plotted over time. Of course, it's also possible to plot it over temperature, but then the signal doesn't look that good because you modulate the temperature. This is why I've splitted this. This is the relating curve for the CP measurement. Again, so you can see here clearly the glass transition for PET at around about 70 up to 80 degrees, and the melting peak here. But just to be sure, the melting peak itself isn't defined in this CP measurement because the CP doesn't get bigger due to the melting. It's just the endothermic effect you can see there. So this isn't really the CP. Normally it must be below, but you can't handle this. The device has to spend more energy and more heat into the measurement cell so far to melt the sample. What's also pretty interesting, what we can see here is the CP after the melting is slower than before. And this is caused by the heat capacity of a liquid is lower than of the same material in solid state here in this case. Let's talk a bit about performance of our CP measurements. So the accuracy of the Chip-DSC with modulated DSC is, I think, so pretty good for a DSC. So we can reach 1 up to 5% accuracy. So this is pretty high, a pretty good value, I think so. And to prove this, here you can see the black curve is the literature value of Sapphire, and the red one is our sample measurement with Sapphire. So yeah, the biggest deviation here is at this point so far, and it's about 1.5%. So I think it's pretty good. What's important at the very first beginning of the measurement and really at the end, the values could differ from the literature because you need a complete modulation just to receive good signals, because you have to evaluate the amplitude, as I mentioned before. What you can see here at the bottom then is our correction curve, the calibration curve, and of course the measurement curve. So this is also an advantage of this device. So the lowest temperature, now it's plotted time, but we can see later in our hands-on, is pretty low for a good CP signal. So you can measure the CP almost from room temperature, unless, of course, you have any cooling option. And so you will receive good results really near to room temperature or your starting temperature at all. So now Sapphire at all is inert. So let's talk about something else than our calibration standard. And this is why I've measured indium. Just to be sure, this is basically the same calibration. So we calibrated with Sapphire with round about 0.7 joule per gram Kelvin at room temperature. And I also measured here indium. And what you can see here is the result is 0.233. And the literature says it's 0.233. Oh, sorry. No, I just plotted here 0.23, and literature says it's 0.233. What we also can see here is the melting peak again. And also here, the CP isn't defined. Yeah, what's also interesting here is the reproducibility. I'm not sure if you can see it, but these are two different measurements I've performed, so the reproducibility is pretty good. And what you also can see here is we receive good results also at 35 degrees. I've mentioned the slide before, so I think that's a pretty cool thing, and this is the reason why the Chip-DSC works that good with temperature modulation. So now maybe another example. This is a bit tricky. It's about liquids for CP measurements or for modulated measurements at all. So of course, it's also possible to do investigations of a specific heat for different samples like powders, granules, or liquids, as you can see here. But what happens at, for example, 100 degrees or above? Of course, the sample evaporates. Due to this, the specific heat capacity gets lower, of course. But we have to figure out what's about the energy of the evaporation at all. But in general, as you can see, it's possible to receive good results here. And regarding investigations for evaporation itself, it's pretty interesting, and also to detect the amount of water in a sample, for example. So now let's come back to our PET measurement. Now here you can find some more information about the measurement and a short evaluation. As I already mentioned, you can find here the glass transition at 75 degrees. Also the melting there at round about 243 degrees Celsius. The sample itself, it was a complete granule with 18.7 milligram, and I've measured, as you can see here, from 30 up to 300 degrees Celsius with a heating rate of 5 Kelvin per minute, a period of 60 seconds, and an amplitude of 1 Kelvin. So yeah, this is a recommendation, for example, here for PET. Of course, you have to adjust your settings to your sample. This is important. Yeah, but at all, these are good settings for a first try for your measurement. And yeah, but the next step would be, I've talked also about the reversing and non-reversing part. So let's go on with this. As you can see here, so these are now 5 curves, and there are some additional information. What I've already told you is the reversing part is basically the same like the CP. So the shape of this curve is basically the same like the CP, just upside down. And yeah, we already see this in the slides before. This is because of the reversing part is basically the CP signal, or it's added there with the reversing parts of our DSC signal. So this is everything we could receive from our temperature modulation so far. So the curves we could receive. At first, of course, the CP, the non-reversing. And here it's interesting. What you can see here at the beginning, in the range of the glass transition, is a pretty small endothermic peak. And this is the relaxation. And now it's possible to evaluate this transition easily with, so you can see, okay, it's just a peak. And it's much easier than before at the raw DSC signal you can see here at the blue curve. Of course, you have to zoom in if you want to evaluate. This is just the scaling of my diagram. What else we can see here is the recrystallization, clearly. And what's interesting here, we can't see this in our DSC measurement itself. There is a second recrystallization near to the melting or in the melting, when all the remaining amorphous parts are getting crystalline before they melt. And yeah, so now it's also possible to evaluate this. The reversing part, basically the same like the CP. You can see here the TG and also, of course, the melting. So this peak is the main advantage, and of course also the hysteresis peak or the relaxation, because you can't find or evaluate them in the blue curve here, so in the raw or conventional DSC signal. So to perform a measurement with the Chip-DSC for temperature modulation, we have some requirements. So you have to make sure you have a good sample contact, because we're heating from the bottom. The heat comes from the bottom of the crucible, so it's pretty important to have a good contact also for powders and granules. And we have a limited sample volume, so this is pretty common with every DSC. But this is important here in this case, so you won't receive a temperature gradient. So please make sure you have a nearly flat sample if possible. And of course, for every DSC measurement, it's important the sample must not react with the crucible material. And yeah, because otherwise maybe you can destroy your measurement system, or otherwise you won't get the results you want to just from your sample itself. And there are basically 3 steps we are performing. At first, we have to run the correction curve. We have to run, for example, a sapphire reference, but of course, it's also possible to use other materials as a calibration. You just have to make sure you have enough literature values. There are some in our software. And of course, the material should be inert within the temperature range you're interested in. And then the third step is you can run your unknown sample. So I already told you we want to do a short hands-on. So let's go to the software maybe. So here we go. Basically, this is our measurement software. Our software itself is splitted into 3 parts. So you have the administration. There you can set up all the materials, for example, the calibration material for specific heat, and also your different devices. And the second part of our software is the measurement software itself. You can see here on the screen right now. So we have our main information like temperature, what sensor we use, and the calibration we are using. And important here for the hands-on is the general settings part. So there are just a few steps you have to perform to make your measurement. At first, of course, you have to type in the name of your measurement. The next would be our weight. If you want, you can enter the customer order number. You have to use your want, and then you can select the type. And here we go for our temperature modulation. The first thing, as I already mentioned, is the correction measurement. So we should make sure we know this is the correction measurement. This information, of course, is also stored in the database with your curve. And what we have to unlock here is the temperature modulation. So, for example, it's possible to use a period of 60 seconds, for some samples also 90 or 120 seconds, or maybe if you use a smaller amplitude, also 30 seconds or something like this is possible. For a first try, we could use 60 seconds here. And of course, we can set up the amplitude, for example, 1 Kelvin per minute. So the amplitude of our modulation itself will be 1 Kelvin. And the next thing we have to add to our measurement is the temperature profile, of course. So in this case, I would heat up with 5 Kelvin per minute up to 300 degrees if I'm interested in PET, for example. So here you have a preview about the average heating rate, so you know how long this measurement will take. Of course, it's possible to do the measurement much faster, but you have to make sure you have enough periods to evaluate, to have a good resolution of your DSC signal. And what I recommend is to use the scheduler. So if you're not sure if there are some bumps near the device, I'm not sure if everyone uses its device in a lab. So I recommend to use the scheduler. For example, we can run it 3 times and start from a temperature of 35 degrees Celsius. So this is how I perform my correction measurement. And then we do the same for the calibration measurement. But now we have to make sure we have the right weight here. So for example, our standard calibration sapphire plate is round about 25 milligram. And you just have to change the type of your measurement. And of course, you have to select the material you're using. And what you can see here is there are already some materials inside you can use for the calibration of your temperature modulation. What else is important? You have to leave all other settings like the temperature modulation and the temperature profile the same. Last but not least, it's possible to perform your sample measurement. And now, of course, you don't know what material is, or if you know it, it doesn't affect the measurement itself. And you have to type in the sample mass and, of course, change the name. Everything else, again, is the same for temperature modulation and also temperature profile. Also here, you just have to start the scheduler and wait until the measurement has finished. Now, let's talk about the results. At first, here we can see PET measurement with conventional DSC. So I already explained. At first, we can see here for this sample the TG. And what we also can see here is the relaxation peak. So especially to evaluate your TG with intersection, the hysteresis peak or the relaxation peak will affect the result for your class transition. So here, again, one of the advantages of the temperature modulation, we can split it with reversing and non-reversing parts. At next, of course, we can see here the recrystallization peak and the melting peak with the line due to the lower CP values. Now let's go for the modulated VSC measurement. Here I've plotted in the upper part of this diagram all the curves we need. So the red one is the calibration curve, the blue one is the correction, other way around. The red one is the correction curve, the blue one is the calibration curve, and the black one is my sample measurement. And just a hint, if you use just the crucible without any sample inside for the correction measurement, the amplitude will be pretty small due to the low heat capacity. With your sapphire inside, the amplitudes of your result, so the DSC measurement itself, gets higher. And Here in this case, I've used, I think, around about 19 milligram of PET with its higher heat capacity itself of around about 1.5 near the glass transition. And so this way, you can make sure, okay, what's the measurement? Of course, it's also possible to plot it in our software. So everything is possible here. Now, what do we have to do for the evaluation? In this case, we have our modulation tool. And now we can select our correction measurement. This is the right one here in this case from last year. And now I can choose one of my many CP calibrations. And so fine, here is our first signal. What's interesting now here is there's much noise on the signal. So what's possible with every software, I think so, you can smooth these curves just for better or clearer results. Basically, you can see everything here. There's the rise for the of the CP due to the glass transition and also the melting. And now let's smooth it. And what you have to keep in mind, if you smooth the curve, you also change the result. So, for example, if you want to smooth over 300 points in this case, you won't see the glass transition anymore. So it's important to use the right smoothing just to make sure you don't change the transitions you can see here on your signal. But now let's talk about the other information we could show here. So it's the non-reversible part, the reversing DSC signal, and of course the average DSC signal. Those two curves I want to correct by baseline. This is a new automatic tool we use here. And now let's plot them, zoom out, and for a better visibility, of course, it's possible to make this curve visible here. And now we can find all information we could receive with our modulated DSC measurement. So the dark red one is a reversible part, the result for the reversing DSC signal in this case. The red one is the average DSC signal. And the blue one here is the non-reversing part of my DSC signal. And also here you can see you can find the relaxation peak, the recrystallization, and the second recrystallization for the non-reversing part. Of course, again, the glass transition, recrystallization, and complete melting point with the second recrystallization for the complete DSC measurement and the glass transition and the melting here in the reversible part of our DSC curve. So what we also can see here, there is not the best type of baseline in this case, but this depends on my modulated measurement. So in this case, I would try to use a lower amplitude just to get better results for a better temperature modulation so far.